On a December morning, the sun rises over Marble Bar, Western Australia. Even as it inches over the horizon, the air shimmers with heat. The glowing disk is distorted, wavering in the mirage that clouds the horizon. It's as if it's reflected in some vast, glimmering pool just out of reach. But there's no water here. In this remote part of the Australian outback, water doesn't last long. The sun ascends through an intensely blue sky with no clouds to obscure its piercing glaze on the landscape below. Shadows shorten and all but disappear as the red rocks bake in its merciless gaze. Long, rocky ridges extend to the horizon, and hills are cut by sharp valleys. But the agent of their formation is nowhere to be seen on this hot December day. The riverbeds are dry, only dust flows along them in the morning breeze. The air is hot, heavy, and eerily silent. Living creatures, from insects to the roaming kangaroos, cower beneath the noonday sun. They seek shade beneath the few sparse acacias that line the barren river valleys. It's a tough existence, but life clings on. Yet those sun-baked rocks preserve a record of a very different time. They are granites, formed deep in the Earth's crust long ago, volcanic lavas that flowed out over the surface, and sedimentary sandstones that accumulated grain by grain at the bottom of an ancient sea. By themselves, the rocks are scarcely remarkable, but their age is what sets them apart. Because this bedrock, shimmering in the heat, is 3 billion years old. This corner of Western Australia is one of the oldest remaining slivers of continental crust from that unbelievably ancient time. And the rocks tell a remarkable story of an Earth wildly different from today. Far removed from the viciously dry and lifeless landscape in which the rocks are exposed, the Earth at 3 billion years ago was a vibrant, balmy water world, teeming with life. A traveller departing Marble Bar today, embarking on a journey 3 billion years into the past, would find themselves on a truly alien world. $3 billion years is an inconceivably large amount of time. It's 1,000 times longer than humans have been on the planet, and 5 times longer than the reign of all animals. But if the entire history of the Earth from 4.5 billion years ago to today were compressed into a single year, then the Earth 3 billion years ago would be living through its very own springtime. Though still young in geological terms, a lot of time has already passed on the planet, entering into its second quarter. And while the changes may have been slow for those first 1.5 billion years, there has still been plenty of time for planetary transformation. From the first specks of dust colliding in a protoplanetary disk, the Earth formed a flaming ball of molten rock. Through the HADEAN, it was unsettled, continually battered and bombarded in a chaotic early solar system. Heaving gravitational forces tore at its fragile crust, opening rifts of flowing lava and shattering the newly formed rock. Only time could allow these wounds to heal as the stray, wandering rocks grew ever fewer in number. The last few thousand impacts delivered a precious payload: water and organic molecules. Gradually, ever obedient to the laws of thermodynamics, the planet cooled. The steamy atmosphere rained and rained, turning puddles into lakes, lakes into seas, and seas into oceans. Bolstered by its watery blanket, the crust solidified into a thick layer of volcanic rock. Meanwhile, the planet's interior remained a scorching, roiling, molten mass. Plumes of liquid rock billowed upwards for thousands of kilometers from the newly formed liquid iron core up to the base of the volcanic crust. They punched through, feeding volcanoes and shattering the crust anew. On the shores of these first oceans, or perhaps in the depths, fed by exotic hydrothermal chemistry, organic molecules form new shapes and new relationships. Coincidentally, this novel chemistry is self-sustaining. It promotes the formation and long-term survival of even more exotic chemistry. And so slowly, incrementally, the stage for life is set. At some point, a few 100 million years after the formation of the Earth, life begins. And so, in a mere 1500 million years, we've seen the planet transformed. From a hellish Hadean, a racked and chaotic mess of hot magma and splintered rock, to the ancient world of the ARCHEAN. Much of what we take for granted on our modern planet, from plate tectonics to our protective magnetosphere, from rainforests to the human race itself, can trace its forebears back to the ARCHEAN. But this ancestral world is still a foreign place. 3 billion years removed from the Earth today. Standing on the surface of the planet, a traveller from our world would find themselves in a disconcerting land of twilight, even when the sun stands high in the sky. The sun itself is scarcely older than the Earth, and it too is in the springtime of its life. Even more so, as the lifetime of a star like our sun is typically 10 billion years, so at just 1.5 billion years old, it's barely adolescent. This young sun is still ramping up, becoming infinitesimally hotter and brighter with every passing day. In the ARCHEAN, it's only 2/3 as bright, and 2/3 as hot as today. But this faint young sun presents the planet with a problem. With drastically lower solar radiation, the Earth should be gripped in an unshakable ice age, plunged into a dim coldness akin to the icy chill that freezes carbon dioxide solid on the surface of Mars. With a faint, young sun, there's no chance of water flowing, or of chemistry working to create life. The dim, noonday twilight should shine down on a snowball planet, frozen from pole to the equator, shining icy white against the blackness of space. But it doesn't. 3 billion years ago, the Earth is a living, breathing planet. The rocks at Marble Bar whisper of cascading rivers, of thriving life, of water cycles and rock cycles in full flow. This apparent impossibility is known to scientists as the faint young sun paradox. That a planet so deprived of warmth can thrive regardless. But the answer to this paradox isn't so hard to find on this very early Earth. The planet is saved from a frozen fate by its atmosphere. Unprotected, any traveller from today would soon asphyxiate, unable to breathe the air of their own planet. Like the Hadean of 1 billion years before, the Earth is still deadly to oxygen-breathing life. In fact, there is no oxygen, and comparatively little nitrogen, both of which make up the majority of our atmosphere today. Instead, the air is filled with a heady combination of carbon dioxide, methane, and water vapour. A toxic concoction to much of life on Earth today, yet one which is responsible for keeping the Earth alive 3 billion years ago. Because these gases, belched from volcanoes and vents all over the planet, have the unique ability to trap heat. They are greenhouse gases, allowing the faint sun's radiation to pass in, but not letting the reflected radiation escape. By swaddling the globe in this insulating blanket, holding onto every scrap of heat the sun produces, the atmosphere keeps the planet warm and the oceans liquid. More liquid oceans to evaporate also means more water vapor in the atmosphere, helping the Earth to sustain its survival blanket over time. And yet, it's not as warm as it could be. Rich carbon stores in the atmosphere and enough heat to power chemical reactions create a dense photochemical haze, just like on Saturn's moon, Titan, today. This haze lingers as a high-level fog, turning the skies orange and dimming the sun's light even more. There are no clear blue summer skies here. The hottest days only serve to thicken the haze and cast a sickly orange gloom over the landscape. This perpetual veil may help the swaddled Earth from becoming too warm by reducing the sun's thin light when the planet's surface becomes too steamy. By day, the skies have a murky pallor, but by night, they come into their own. Although the stars may not be visible, the night skies are bright with another kind of light, the auroras. Today, green and red curtains of light are occasionally draped across the north and south poles, as the powerful solar wind penetrates the Earth's magnetic field, energizing the oxygen and nitrogen in the atmosphere until it glows. These beautiful auroras are the serene consequence of our planet's magnetosphere, repelling and rebuffing the sun's never-ending particle stream, protecting the surface from the worst of its effects. Although scientists still aren't sure how it's generated, now or in the past, there is evidence in the rocks that this magnetic shield has been protecting the Earth for around 3.5 billion years. But the auroras on the Archean Earth would have looked very different to today's. The colour of these ephemeral curtains depends on the gas that's being harassed by the solar wind, and because the composition of the atmosphere was different, so too would the auroral light show differ. Instead of green and red, created by energetic oxygen and nitrogen, the skies would shine electric blue. As the carbon dioxide, so abundant in this early atmosphere, is bombarded by the sun's gale. These blue curtains may not be restricted to the poles either. The planet's magnetosphere is generated deep within the Earth by the flowing of the liquid iron outer core around a solid inner core. But 3 billion years ago, the inner core had not yet formed. The centre of the planet was still too hot for the metal to solidify, despite the crushing pressures. So the liquid in the centre was unconstrained, and the magnetic field it generated could have been similarly chaotic. Geomagnetic poles could shift across the surface, or there may be no consistent pole at all. Without a single weak point in the planet's magnetic shield, the solar wind could penetrate the Earth's defences at any point on the surface, draping auroras over skies from the equator to the pole. But it isn't just the nightly illuminations that are colour shifted thanks to chemistry. Beneath the hazy orange daytime skies or the rippling blue curtains of nighttime, the planet's oceans are tinted a murky green. Water itself is colourless, or blue tinged with depth as the light from the surface is scattered and dispersed. But in these early oceans, the water is rich in iron too, pumped out of hydrothermal vents or delivered by eroding rivers. In our oceans today, iron doesn't stick around long, instead reacting with oxygen from the atmosphere or being assimilated into living things. But without oxygen in the early atmosphere, the iron can linger in its dissolved state in the oceans. There, other chemical reactions combine to transform it into a fine green rust. And when this rusty green iron fills the oceans, it turns them a sickly green. And there's a final chemical clue in the 3-billion-year-old rocks from Western Australia that helps to paint a picture of an alien ancient Earth. Scientists have carefully measured the abundance of a particular heavy oxygen isotope, which is rare in our oceans today. This heavier form of oxygen, carrying 2 extra neutrons in its nucleus, is preferentially locked away in clay when continental crust is weathered. Modern oceans have little of it, and the rocks that form at the bottom of these oceans are correspondingly depleted in heavy oxygen. But in the 3-billion-year-old crustal rocks, levels of this isotope are boosted, implying that the oceans themselves contain lots of this heavy oxygen, compared to its normal form. Why should the ratios be so different over time? Scientists think it's because the Archean Earth lacked continents to absorb the heavy isotope. The 3-billion-year-old Earth was a water world, almost entirely covered by these bizarre green oceans. We may think that the planet today is dominated by seas, but they cover a mere 70% of the surface. Imagine instead a smooth sphere of water, peppered with the occasional black volcanic island or archipelago, but entirely lacking any significant landmasses. This ancient, colour-shifted ocean planet is our home, but it's discomfortingly alien. And yet, beneath the water's surface is a phenomenon that is more familiar, and as far as we know, uniquely earthly. Descending beneath the surface of the oceans, a time traveller would discover a hive of activity, albeit microscopic. Individual life forms are so small as to be invisible, but the sheer abundance of life in these Archean oceans is visible if you know where to look. And the trick in looking for life here is to look for the energy. All life needs a supply of energy to support its metabolic reactions, and these early life forms are no exception. On the slopes of volcanic islands, submerged deep beneath the waves, are systems of hydrothermal vents. Linked to the hot magma deep in the crust by a spidery network of cracks, water circulates and pumps hot, dark, metal-rich smoke into the green-tinted waters on the sea floor. The metals and minerals accumulate around the vents that disgorge them, creating towering chimneys that rival an industrial revolution skyline. And around these chimneys is life. The walls are coated with a thick but indistinct fuzz. These are the cities of the Archean oceans. Within that nebulous mass are thousands, millions, billions of microbial life forms, huddling close to the vent, feeding off the reactive sulfur compounds that settle out from its billowing smoke. The energy released by breaking down these compounds is used by these denizens to keep them alive and allow them to continually increase their population. By modern standards, this vent is an inhospitable refuge, dark and scorchingly hot, approaching 100 degrees Celsius. But to these microbes, it's all they know, and all they need. Having evolved over millions of years in this very environment, they are genetically suited in their own minuscule way. Their genes help them withstand the searing temperatures, and their metabolism craves only the minerals that the vent supplies. Without competition or anything larger to prey upon them, their cities can sprawl, colonizing any chimney or vent on the ancient sea floor. Not only are these microbial colonies sprawling, but they are also high-rise, a stratified hierarchy of slightly differing species, each with their own specialization. Held together by a sticky extracellular goo, these microbes form multicolored layers wrapped around the hydrothermal chimneys. The lowermost social stratum deals with the hottest temperatures and the purest chemical ingredients. Ascending through the levels, successive populations feed on different chemical products, each deriving energy from the waste products of their neighbors. It's a complex, interconnected metropolis, writ small around every hydrothermal vent. It may be bacterial utopia around these chemical chimneys, but after a few 100 million years of colonization, it's getting crowded. New life forms continually need to innovate to find new sources of energy, new niches at the edge of the vent city. Other parts of the ocean are less appealing, lacking the dense concentrations of minerals that these first microbes rely on for energy. But there is still energy, of a different kind. Closer to the water's surface, there is light. The light from the faint sun crosses interplanetary distances, pierces, much diminished, through the photochemical haze that blankets the sky, and penetrates a short distance into the green cloudy waters. In the shallowest waters, the sea floor is dappled with dim sunlight. The majority of the vent community would not be able to make use of or even notice this new energy source. But a chance mutation in a microbial suburb opens up a new metabolic pathway, allowing the use of light instead of chemistry for energy. These are the very beginnings of a process that will transform the living world. Photosynthesis. The light is still dim, the light-based metabolism inefficient compared to the lush abundance at the vents. It's a stumbling start at best, but it allows this new mutated life to cling on and make anywhere the light touches its home. The stacked urban planning of the hydrothermal cities won't work for this light-based life form though. Instead, the microbes spread out flat, covering every stable, lit surface. They create wide microbial mats, still held together by extracellular glue, but over vast horizontal planes, following the rise and fall of the shallow sea floor. Passing waves and tides wrinkle and tuft them into spidery patterns, and when a strong current tears the mat apart, it self-heals quickly, spreading to cover the surface once again. But these rural expanses of microbial mat have a weakness. A mere dusting of fine sediment washed down from the shore or by a river flood can be fatal to the entire community. The particles cover the mat, sticking to its binding glue, and block the dim light that the microbes rely on. Probably, the first communities to be blighted by this sediment rain simply died, and the new surface later colonized. But in the quest for survival, these evolving communities innovated once again, learning to sense the light through the sandy blanket and growing up through it to emerge at the top once again. In this way, the light-craving microbes learned to build upwards, layering their mats on top of successive sediment veils and always inhabiting the penthouse suite. This type of structure is known as a stromatolite, and they will become a defining feature of the microbial biosphere. They will be found in rocks spanning billions of years, as domed, abandoned skyscrapers entombed within the sediment. Wherever they are found, paleontologists see the echoes of a thriving seafloor community. Incredibly, on this ancient, alien world, microbial life forms are carrying out a niche that they will keep hold of and spread out from over the next 3 billion years. These microbes still exist today, almost unchanged from these original forms. On this strange, multicoloured, hazy planet, they are setting the stage for all evolution to come. You've been watching the entire history of the Earth. Don't forget to like, subscribe, share, and check out the other videos on the first 1.5 billion years of Earth's history we've already released. As always, let us know what you think in the comments, and we'll see you next time.